Composite structures can be made of virgin or recycled feedstock. To accelerate the transition towards circular economy, it is essential to understand why the properties of recycled feedstock matter and how we can measure and verify the essential properties. The material requirements of a product are naturally defined by the targeted end use. Also, some of the criteria may come from legislation or product-specific standards. An example are the interior parts of a yacht or a train, which have strict specification for the smoke formation in case of fire to improve the fire safety of the vehicle. The specifications can be divided into technical material requirements and aesthetic ones. In general, the technical material requirements can be classified in mechanical, thermal, chemical, optical, and electrical properties. Depending on the application of the material, some of these properties might be more relevant than the others. The integrity of a composite structure is often its most important feature, and therefore the mechanical properties are of great interest. For example, composites can be classified in the structural, semi-structural, and non-structural composites based on the application-specific level of the mechanical requirements. The requirements are very high for an airplane wing, which is an example of a structural composite. Instead, the importance of the mechanical properties is lower for the instrument carriers of cars, which are examples of semi-structural composites, and even lower for some train interior parts, which are non-structural composites. Once the mechanical properties of the composite are proven sufficient, also other relevant properties are considered in the specifications. The material requirements for composite feedstock, namely the fibers and the matrix, are defined by the specifications and requirements of the final composite structure. In addition, some material requirements can be related to the processability of the constituent materials during composite manufacturing. When switching from linear to circular economy, a favorable option would be to use the same manufacturing method for recycled feedstock as what is used for the virgin one. However, this is not always possible. Further, the reusability or recyclability of the composite structure after its use might lead to some additional material requirements. It's also possible that the material requirements are contradictory and some compromises must be done. Basically, the material requirements are the same regardless of the origin of the feedstock, but there are some special aspects to be considered when recycled feedstock are used. In fiber-reinforced composites, the fibers and the matrix play different roles. Therefore, also the material requirements of these components are different. The fibers bear the loads subjected to the composite, whereas the matrix keeps the fibers together, gives the composite structure its shape, and transfers the loads to the reinforcing fibers. Also, the matrix dominates the thermal, chemical, and environmental resistance of the final composite structure. The interface between the fibers and the matrix can be considered as a third constituent component of a composite structure. It plays a major role in transferring the loads from the matrix to the fibers, and therefore also its properties are fundamentally important. It affects greatly to the mechanical properties of the composite structure, but it also affects its resistance to chemical environments and humidity. When using recycled feedstock for the matrix, the chemical and physical properties of the material are of great importance. For example, in the case of recycled thermoplastic matrices, the molar mass and the purity of the material might have decreased during its original use and recycling process. These changes influence its processability and the final properties of the second generation composite. To give you an example, the degree of crystallinity of a thermoplastic depends on its purity. Thus, recycled materials might have different degrees of crystallinity compared to the virgin ones. A difference in the degree of crystallinity leads to changes in mechanical, thermal, and optical properties of the matrix, and therefore also changes the properties of the final second generation composite. To achieve a similar degree of crystallinity for the second generation composite, it might be essential to modify the process parameters. Also, additives can be used in second generation composites to mitigate some issues originating from the recycled feedstock materials. However, recycled thermoplastics are supplied in a similar form of granules as virgin feedstock, and therefore they are easily implemented in existing systems. Thus, they can most often be processed with a similar manufacturing system as long as the viscosity and the flow of the material at the processing temperatures are sufficient. The physical form of the recycled fibers vary greatly from the virgin ones. Virgin fibers are typically supplied as a continuous fabric or roving, whereas recycled fibers are most often discontinuous because the limited size of the original composite structure and the applied recycling technology. The different physical form of the recycled fibers prevent the use of the same manufacturing methods as well as the characterization methods that are used for virgin fibers. For example, the recycling methods might reduce the size or the length of the fibers so much that it's not possible to use the same measurement methods to test the tensile strength of individual fibers or yarns that are used for virgin materials. Therefore, comparable data might not be available for recycled fibers as what it is for virgin fibers, which must be considered when designing second-generation composites. The important material properties of the fibers are the fiber length, which affects the processability, and the mechanical properties of the final composite structure, as well as the mechanical properties of the fibers. Also, the surface quality of the fibers is very important for its strength. The recycling process may compromise the integrity of the fibers, introducing wear and defects on the surface, which not only diminish the fiber diameter, but may also generate some defects and initiate fractures. This deterioration will lead to lower mechanical properties of the fibers. To ensure a compatibility for the fibers and the matrix and an efficient load transfer at the interface, the surface of virgin fibers is treated chemically. This treatment is called sizing, and it can be optimized for a specific matrix chemistry. In addition, the fiber matrix adhesion, the sizing improves the processability of the fibers and protects them during the manufacturing of the composite structure. When virgin fibers are used, the composite manufacturer can rely on good adhesion at the interface if the selection of the sizing is done according to the matrix. However, certain recycling processes of fibers, such as thermal and chemical fiber extraction processes, remove the sizing from the fiber surface, which leads to poor interaction at the fiber matrix interface and also poor mechanical properties for the second generation composite structure. Also, the absence of the sizing might make the fibers very difficult to handle. To ensure good quality composites, it might be essential to use some additional surface treatments for the recycled fibers or use some additives in the matrix material to enhance the compatibility of the fibers. One distinctive feature of recycled feedstock when compared to the virgin feedstock is the variation of the material properties within a feedstock batch and between the different batches. The original manufacturing method of the composite structure, its exposure to external loads, its lifetime, and the recycling methods used all affect to the material properties of the recycled feedstock. Therefore, there are inevitably several factors that affect the final characteristics. Variation in the properties of the feedstock material might lead to variation of the properties of the final composite structure. Considering that the properties of recycled feedstock might be lower than the properties of virgin materials, and there might be some variation in these properties and some need for additional treatments, it is very important to know the characteristics of the recycled feedstock well. Therefore, it is also very important to know how these properties can be measured in a reliable manner. Based on a reliable information, the user can make well-informed decisions how and where to use the recycled materials. For example, it might be that recycled fibers from a structural composite might be applicable only in semi-structural composites. Also, based on the reliable data, the user can estimate the total environmental effect of the composite structure, considering the positive effect of recycled feedstock, but also the effect of possible additives or additional surface treatments required.